Hello, my name is Justin Cole. I'm a student at the University of Colorado, Colorado Springs, and I'm a junior majoring in data analytics and systems engineering. Today I'm going to be making a video lecture to demonstrate how to perform something called a t-test, or three different kinds of t-test really, in a software called SPSS. We're going to talk about what all of these different things mean. So let's go ahead and dive right in. I'm going to go ahead and share my screen to a whiteboard. All right. And let's go ahead. Get a text. Oh, that's odd. Marker, text. Boom. There we go. So let's go ahead and ask an initial question. What is a t-test? So a t-test is something that is used in kind of a subfield of statistics called inferential statistics. And inferential statistics is kind of the field that's used anytime that you're trying to draw conclusions about a population based upon data about that population, kind of like imperfect, incomplete, just taking samples, that kind of thing, and then extrapolating from there. So a t-test is used in something called hypothesis testing. We're going to be making hypotheses today and testing them to determine, things about a population or several populations, in fact. But the t-test is used in hypothesis testing, which is where we try and test an idea to draw a conclusion about a population. So a t-test is an inferential statistic, it is one of the most commonly used inferential statistics in the field of statistics. And today we're going to talk about three separate kinds of t-tests. So the first one is called a one-sample t-test. The second one is called an independent samples t-test. And then the third one is called a paired samples t-test. So I'm going to go ahead and write those down. One sample t-test, independent samples t-test, and then finally the paired samples t-test. And these are not the only three kinds of t-test. There's also there's two different kinds of independent samples t-test, and today we're only going to be speaking to students t-test, which has some fun history if you're interested in looking it up at the Guinness Brewery in Ireland. But yeah, so let's go ahead and break out some formulas here to kind of establish what we're looking at and how we arrive at these numbers. So we're not going to be doing any proofs today, but let's go ahead and see what kinds of variables are being involved. So let's go ahead and start off with the one sample t-test. So when would we use the one sample t-test? Well, there's one last thing that I meant to mention actually about t-tests as well. We use t-tests anytime we are trying to compare the means of two groups. And in the case of the one sample t-test, we only have one group and we're comparing it against some reference variable. So we'll speak to some examples later, but a really common example that I've seen is, let's say that you're working at a cafe and you're supposed to have a certain, like if you pull out one shot of grounds for espresso so that you can pull a shot of liquid espresso, those grounds are supposed to be about the same mass every time. So let's say it's 75 grams or something. So you want to go ahead and make sure that that espresso grinder is releasing 75 grams or thereabouts, at least on average 75, to make sure that you're producing a consistent product. So let's go ahead and write up a formula. This comes from our textbook on page 387. We're going to talk about these symbols as we go as well. T, or our t value, also our t values get converted into p values so that we can interpret things and have and draw conclusions about these numbers that we're talking about. But that t value is equal to x bar, which is our sample mean of our data, minus mu, which in this case is some known reference variable. So like that 75 grams in the cafe or something, we want it to be that. That's the standard. And that is divided by lowercase sigma, that's the standard deviation, over the square root of n. And that's the square root of just our sample size of this sample right here. So fun fact as well, everything in the denominator here is also called the standard error, or SE. But that's all the information that you need to compute the t-value in the one sample t-test. Now let's go ahead and talk for a second about the assumptions of the one sample t-test. So we can't just use the one sample t-test on any old data that we want. This is a, I'm getting this right, this is a parametric inferential hypothesis test. So for this, we need to make sure of two things. First off, that the data upon which we are using this test is normally distributed, so continuous, and the Gaussian distribution, or whatever you want to call it, the bell curve. And you can't just eyeball that. It's important to go ahead and computationally verify that what you're looking at is a normal distribution. We're going to go ahead and do that later as well in the software. And then there's another assumption, and the independence of the variables involved. This has less to do with like computationally verifying something, and it has more to do with just experiment design. So making sure that your variables don't influence each other in any ways that could be disadvantageous here. As an upfront, all of the tests that we're going to do, the independence is going to be well baked into the experiment design. So let's go ahead and next talk about the independent samples t-test. And again, this is specifically the student test. So when will we use the independent samples t-test? It's a really good question. So we want to use the independent samples t-test anytime we are comparing the means of two different groups. So it sounds kind of similar to the overall definition of a t-test. Let's get more specific with an example. And there's this really common example that I've seen in textbooks and online videos and stuff like that. Let's say that you've got two different groups, and both are people of any ages and backgrounds, but all of them are experiencing hypertension. So let's say that we are a pharmaceutical researcher and we've developed a new drug that may improve their blood pressure. So group one, we don't give them any drug, we give them a placebo. And then group two, we give them our hypertension drug. And we then collect data on all of them after they've been taking this drug for a while, and it should be in effect. We measure all their blood pressures, and we see if there is a statistically significant difference in the means of the two groups. And we would do that using an independent samples t-test. So let's look at the formula here to kind of see, again, computationally what we're really looking at. So here, we're once more going to have t is equal to, and again, this is for the independent samples t-test, this is going to be x bar sub 1, that's the sample mean of our first group, minus x bar sub 2, it's the sample mean of our second group. And these don't have to be in any particular order. I have also seen some conflicting information that some people say this is absolute value. The textbook that I'm referencing, at least, says that it is just the difference between group 1 and group 2. So you could choose either one to go first, just to keep it positive, or you could take the absolute value. I think interpreting negative t-test values or t-test results isn't particularly complicated. But then we're going to have, so we had the SE up here, the standard error, and it's going to be the standard error of the same down here. So there's some similarities between these two formulas. So the standard error of the sample mean of group 1 minus the sample mean of group 2, or at least the difference between the two. And I mean, if we wanted to represent what this really is computationally, right here, this is the same as standard deviation of group 1 over the sample size, the square root of the sample size of group 1, minus the standard deviation of group 2 divided by the square root of the sample size of group 2. So that's what that is. But we could also just write it as SE parentheses and then those two. So let's once more talk about assumptions. So the assumptions for the independent samples t-test are the same as the one sample t-test with one extra assumption. So first, we need to make sure that this data is normally distributed. Second, the variables need to be independent of one another. And third, we need to have something called homogeneity of variance. And that's something that we're going to talk about how to do in SPSS later. But what does this really mean? So the variance in statistics is the square of the standard deviation. Uh, so V equals lowercase sigma squared. But or is it R? Oh no. Okay, it's either V or R, but don't quote me on that. You can Google it. Um, anyway, so when doing an independent samples t-test, we need to make sure that the spread of the variances between the two groups are equal. They're comparable. So we'll talk about how to do that later with a test of homogeneity of variance. Finally, let's go ahead and talk about the paired samples t-test. So the paired samples t-test is used often in like a before and after in a group. So let's say that somebody's trying to test a weight loss drug. They take a population of people and they measure all of their weights or body fat percentages or whatever, um, and they take the mean of that, and then some time passes after they've, let's say, like taken a drug or followed a workout routine or a diet or something like that, or a combination. That'd be complicated. But anyway, after, and then you measure all of their weights or body fat percentages or whatever you want, and you measure the before and after. And this also has a formula. It's going to look similar. T equals D bar. This is the mean of the differences between the before state and the after state. So you subtract all of for every entry, you subtract the after by the before, and then you have this new data set that's just differences, and then you take the mean of that, and then you also find the standard deviation of it, and that's where we get this standard error. I'm going to go ahead and write this out though because it's going to be more simple. Or sorry, we don't need that hat. And you're going to divide it by sigma sub d, that is the standard deviation of all of those differences, minus, and then once more, the square root of the sample size. So by a cap n. So finally, let's go ahead and talk about some assumptions here. The assumptions for the paired samples t-test are the same for the one sample t-test. We only need to verify normality and independence. So that is a brief overview. From here, we're going to talk about the software that we're going to be using. So I'm going to go ahead and share my screen over there. I actually need to reboot this because this is my second take and I had to close out all of my applications previously. Zoom is a little finicky for this. Okay, sweet. Share. Boom. Here we are, SPSS. So today we're going to be doing these tests in a software package courtesy of IBM called SPSS. And SPSS stands for the Statistical Package for Social Sciences. So I'm going to talk about some brief history with SPSS, kind of contextualize what it is and how it came about, talk about why I chose to use it and some of the strengths and weaknesses of SPSS compared to other softwares, and then maybe talk briefly about the UI. So first off, SPSS was first released in 1968, and it was originally written in Fortran, and it was made by this company called SPSS Incorporated. So here, just to speak to the UI really briefly, it looks a lot like, if you've used Microsoft Excel before, it looks very similar to that. We have all of these cells, we have these tabs down here in the bottom left corner, but here we don't have sheets like in Microsoft Excel. Instead, we have these different views. So here in a little bit, you're going to see I'm going to import all of my data, which I made in Excel. We'll talk about that in a second. I'm going to pull all this data into my data view, and then I can click on variable view to see information about the variables that I've pulled in. So in 2009, SPSS Incorporated was purchased by IBM Corporation for $1.2 billion US. And today, IBM is still caring and feeding for the software and all the users and the community. Um, and at this point, SPSS is one of the front runners for statistical analysis across not just different industries, but different sectors of civilization. So you've got people in government using SPSS, people in academia, people in industry, people everywhere. And what it really is used for is fundamentally statistical analysis and research. And it's also very good for things like data mining as well. So let's talk a little bit about the strengths and weaknesses of SPSS. Um, so the main strength that I have observed in the community that I've found online that speaks to it, and my professor for this course that I'm taking right now, that I'm making this video for, is that SPSS is arguably the most powerful and also arguably the most user-friendly statistical analysis software out there. Um, it it is an absolute powerhouse, and it's very intuitive to use. For most of this course, we've been using a programming language called R for statistical analysis. And already in the couple of days that I've been using this, I prefer this, even though R is fine as well. But the main weakness of SPSS, so I mean, if it's so great, why doesn't everybody use it? Well, SPSS is a commercial software product. Right now, I'm using the trial version courtesy of IBM, so thanks to them for that, making that available. But there are licensing fees as soon as my trial, ends. So it's expensive. The cheapest option for an SPSS license is $99 a month. And for me, a college student, that's somewhat cost prohibitive. So, and that's also, again, just the cheapest. That is, you're getting the basic package, not any of the extra add-ons, the bells and whistles. So I also want to speak to why I chose SPSS rather than SAS for this assignment, because that was the alternative that we were allowed to choose. I heard that overwhelmingly SPSS was used more than SAS. And I also heard that it was more user-friendly. So just given that it's the more commonly used of the two, I like having transferable skills and I wanted to get exposure to it. So yeah. So next I want to speak to the data that we're going to be using today. So there was a bit of a challenge. I spent a handful of hours looking for normally distributed data that would be suitable for the use of these 3 different t-tests, just like surfing the open internet for open source data. And I had a lot of trouble finding stuff that was relevant and normally distributed. And maybe I just don't have the statistics chops yet to be able to circumnavigate some of those challenges, but we'll get there. So here's what I chose to do. I chose to generate simulated data, normally distributed data, in Microsoft Excel, just using a random number generator that generates within the boundaries of a normal distribution. It just needs a mean and a standard deviation. So, I'll even show you here actually. New share. This is what we're looking at here. Those are all of my data sets we're going to be pulling in. So I'll go ahead and share back to, there we go. All right. So let's go ahead, now that we've talked about our simulated data, let's go ahead and get into our first real t-test. So let's import our first data set. So to do that, I already have everything mapped to, I already have SPSS mapped to my drive on my computer. So I'm just going to go to File, Import Data, and everything that I have is just, I made it all in Excel workbooks. But you can pull in all different kinds of files in here, CSVs, text data, SAS data. I'm trying to remember what the file format is, but they have their own proprietary format, which you can find in ample amount across the internet. Anyway, so I'm going to go ahead and hit Excel. And I've already mapped it to the folder where I'm keeping these Excel workbooks. And I'm going to click on this first guy. And yeah, that looks good. Okay, I'm going to reshare my screen. Cool. So now you should be seeing our data as it stands. Now, we're doing a one sample t-test, but let's go ahead and describe a scenario that I wrote for this data. So let's say this data is from a company that sells silver bars. They want to make sure that their equipment and processes are producing bars that are 80 grams on average. each entry here is the weight in grams of a silver bar that was produced. So this is kind of like a quality control testing scenario here. So one sample t-test, right? We have some assumptions that we need to make sure we are correctly making before we just dive into the t-test all willy-nilly. And those two assumptions were normality, so this data needs to be normally distributed, and independence. Now, independence, we know that we don't have any dependent variables in here that we need to worry about. We do know something, though. We do know that all of this needs to be 80 grams. So in that formula that we saw earlier, that mu is going to be 80 grams. That's how it's going to be calculated. So let's go ahead, and before we do anything, let's verify our normality. We can look at this data, and it looks like, we've got some 90s and some 70s, and I think the ballpark is going to be somewhere in the 80s, but we can't just eyeball it. We have to look at this computationally and say that it's normally distributed with a high level of statistical significance. And to do that, there's actually a test in inferential statistics for exactly that purpose. It's something called the Shapiro-Wilk test. So the Shapiro-Wilk test is a hypothesis that is applied to a sample with a null hypothesis that the sample has been generated from a normal distribution. And this was with about, like a 5% confidence interval. If the p-value is low, then we can reject the null hypothesis that it is normally distributed and say that the sample has not been generated from a normal distribution. So we're going to go ahead and run a Shapiro-Wilk test on this. And here's how we're going to do that. We're going to go to analyze, this dropdown right here, and then we're going to go to descriptive statistics and then explore. And now, just want to make sure I'm still screen sharing the right stuff. All right, sweet. All right, I'm going to go ahead and throw my number in the dependent list. For plots, I want to click normality plots with tests. So this is saying I want to test whether or not this data is normally distributed using the Shapiro-Wilk test. And let's go ahead and get a histogram in there too to get eyeballs on this data. So this is about all ready to go. We're going to hit OK. And now a new window has populated. And at this point, I'm just going to share my whole screen. Okay, sweet. So here's what we're looking at. So we just did a test of normality, and we can see down here what that put out. So here we have Shapiro-Wilk, and we have our statistic, our degree of freedom. We have 19 entries, so that tracks, and our significance. Now, if we have a significance below 0.05, then this data is not normally distributed. So because it is greater than 0.05, this data is, we can say with a high level of statistical significance, normally distributed. And we can even get a look at this data. It looks like it could be a little skewed, but I trust what it's saying. So I'm going to go ahead and close that out. So we have now verified that this data is normally distributed. So we can do a one sample t-test. How do we do that? Well, we're going to go back. I swear, the analyze dropdown is the only dropdown I've used for this entire project. It seems like there's a lot of good stuff in here. So I'm going to go to analyze, compare means and proportions, one sample t-test. And I'm going to select num, hit this arrow, and throw it into my test variables. Make sure that we're at a 95% confidence interval percentage. Looks good. And we're going to go ahead and hit OK. All right, so we just did a one sample t-test on this data set. How do we interpret the results? Now, again, our question was, are we producing 80 grams on average? We need hypotheses against which we can test the results of this test. So let's describe our hypotheses really quick. Our null hypothesis, or H0, is going to be that, and I want to make sure that I get this right, that our sample mean is equal to our reference value of 80 grams. With a high level of 95% confidence level of just as we specified earlier. Our alternative hypothesis is going to be that our sample mean does not equal 80 grams. So let's go ahead and let's see how we can interpret the results here in this window that's populated. So here we have one sample test. So our significance, our two-sided p-value for the result of this test is less than 1/1000th, of a percent. So Do we really care about that? Maybe, but we need to have something in hand called our critical value. The critical value is 1 minus the level of confidence that we're looking for. It's 100% minus 95%, so it's 5%. Translate that into a decimal, and it's 0.05. So if our p-value is less than 0.05, we retain our null hypothesis. And then if our p-value is greater than 0.05, we reject the null hypothesis and retain the alternative hypothesis. So we see that our two-sided p-value output of this t-test is significantly less than our 0.05. So that means that we retain the null hypothesis that on average, in this data set, the weight or the mass of these silver bars is 80 grams. Now, I guess as a point of humor, and this is partially in the way that I designed this, but if I were looking at a company that was, producing bars that were this inconsistent but still 80 grams on average, I would want them to rethink their, either their processes or their pouring practices or whatever. But anyway, so that is the one sample t-test. Now let's go ahead and discuss the independent samples t-test. So to do that, I'm going to import the second data set. So we're going to go to File, Import Data, Excel, Independent Samples Sim Data. Sweet. All right, and now we have a new data set. Looks great. So here, let's go ahead and we have some more numbers and different variables and everything, but again, I've got a scenario to kind of describe what's happening to illustrate what we're doing here. So here I want to test the hypothesis that blue-eyed Uber drivers, which are group 1, signified by these guys, have different ratings, average ratings, than green-eyed Uber drivers, which is group 2. So here we have group 2. And they are of equal number. So let's go ahead. We've asked our question. We still need to go ahead and verify that this is normally distributed data. So once more, we're going to go to Analyze. We're going to go to Descriptive Statistics, Explore, throw rating into our dependent list. Plots, we're going to check normality plots with tests and histogram for fun. And we're going to hit OK. And once more, we are looking to see that, where do we go? Test of normality. Okay, Shapiro-Wilk, we are well within statistically significant range saying that these data sets are normally distributed. So we can go ahead and press. And we know based upon our experiment design, which I kind of gave up front, we're saying that these variables are independent of one another. So there's that third assumption that we need to rely on in the independent samples test, or the third assumption that we need to verify, and that is homogeneity of variance, right? So to be able to assess homogeneity of variance in SPSS, we actually need to go through and just do the whole independent samples t-test, and then it comes at the end. So we're going to go to Analyze. We're going to go to Compare Means and Proportions, Independent Samples t-test, and then our test variable is rating. And our grouping variable is group. I use these arrows to transition them over. I could push them back too if ever I make a mistake. Here, it's group. It's got question marks. It's like, how do you want me to group these? Based upon what? And I'm going to hit define groups. And I'm going to say, use specified values. Group 1 is going to be identified by number 1, and group 2 identified by number 2. So hit continue. You see that that's changed and updated. Now we're going to hit OK. Alrighty. So I'm going to maximize that. So first, let's go ahead and look at homogeneity of variance. Where can we find that on this page? So it's here underneath independent samples test, you have Levine's test for equality of variances, and we have our significance. Our significance is above 0.05, which means that these variances are homogeneous with a high level of statistical significance. So we can go ahead and look at the results of the independent samples t-test. Now, what are our hypotheses here? So for this experiment, our null hypothesis is that the mean of sample, or the sample mean of group 1 is equal to the sample mean of group 2. And so if our p-value is less than 0.05, then our means are not the same in a way that is statistically significant. And then our alternative hypothesis is that the mean of sample group 1 is not equal to the mean of sample group 2. And that's if our p-value is above. So we're going to go ahead and look here at our two-sided p-value. And both of those are, again, well below 0.05. So we are, let's test. Okay, sweet. Yeah, so we are going to go ahead and sorry, I'm just double checking this. Yeah, so we're going to go ahead and retain the null hypothesis that these are like within enough of each other to where they're about the same. Even though we can see some difference here, it is not a statistically significant difference. So that is the independent samples t-test. Finally, we're going to go ahead and do the paired samples t-test. So I'm going to go ahead and open or import that data. Excel, paired samples t-test. Okay, cool. Now let's go ahead and talk about this. So what is this data? What is the scenario here? Here in this group, this data is from a group researching the efficacy of a muscle building supplement. So it's known that people can put on up to around 2 pounds of muscle annually if they're working out and doing like strength training and all of that consistently. And that's kind of the upper threshold of what people can achievably do. So here you can see the amount of muscle in pounds that that a group of individuals put on in a year before and after the introduction of a supplement that claims to promote muscle growth. So before, this group is for 1 year before they used the started using the supplement. So it's full 12 months of muscle growth. These are the total amount of muscle growth for each of these individuals in that year without the supplement. And then after is muscle growth in the second year after supplementation. So this represents 12 months of muscle growth with this supplement. And we want to ask, is there a difference between these 2 years due to, in any way that we could attribute to the use of this supplement? So how are we going to do this? Well, again, we have 2 assumptions here, normality and independence. And we're going to test normality really quick. So analyze, descriptive stats, explore. We're going to add before and after to our list, plots. We're going to hit normality test and histogram for fun. Then we're going to hit OK. So this pulls up this window, and really the good stuff that we're looking for is the tests of normality, Shapiro-Wilk. We are well in statistically significant range that these are normally distributed bits of data. So feeling good about that. And we're going to go ahead and press with a paired sample t-test. So how do we do that? We're going to hit analyze. Then we're going to go to compare means and proportions, paired samples t-test. I'm going to add before, after to our paired variables. Options, double check 95. Yep. Estimated effect sizes, standard deviation difference. All right, cool. And we're going to go ahead and cruise in. Hit OK. All right. So we have our paired sample t-test and our significance. Now let's talk again about our hypotheses. So our null hypothesis here is that the mean of the difference between the pairs is 0. And so that's saying that there was no big difference before and after. The alternative hypothesis is that the mean of the difference between the pairs is not 0. So let's go ahead to paired samples t-test and look at our two-sided p-value. And we see that here. Okay, there we go. You can see that the two-sided p-value is substantially lower than our 0.05. It's around, less than 1,000th of a percent. So we are going to go ahead and retain the null hypothesis that the mean of the difference between the pairs is 0. So there we go. So we're saying that there is no statistically significant difference between these two groups. So that is the last of our tests. I'm going to go ahead and stop sharing that screen. And I just want to conclude really quick, kind of wrap up a lot of the things that we've been talking about. So today we talked about the t-test, and the purpose of the t-test, just to recap, is to compare the means of two groups and identify whether or not there is a statistically significant difference between them. We also talked about how to perform three specific t-tests: the one sample t-test, the independent sample t-test, and the paired sample t-test. And we did all of that in a statistical analysis software that is made by IBM called SPSS, which again stands for the Statistical Package for Social Sciences. Yeah, thanks for watching. I'll probably post this on YouTube, so I guess ding that bell and smash that like button. I've never posted a video before, but this will be fun. And yeah, have a great rest of your day.